Today is the day. Today, it's finally here. The day where we get to use the black magic of the Laplace transform, which is a new technique to solve differential equations. And we're going to use it to take an ordinary differential equation for a function you want to find, little f, as a function of time, which is really hard to solve, right? ODEs are really hard to solve. It would be great if there's some other technique where we can blast it over into a new dimension where we replace time with a Laplace variable s for a different function, capital F, as a function of a Laplace variable s, where it is an algebraic equation, which algebra is much easier to solve than an ODE. And we can solve that and blast it back into the real space, the time that we live in, and get the function that you want. If there is such a technique, that would be pretty amazing. And today, we are going to do that. So let's do a quick example en route to doing what we want to do today. Quick example. Suppose we want to take the Laplace transform of the function t, just plain old linear growth as a function of time. What would this be equal to? Again, let's use the definition. Just like that. Now, I know it's kind of cumbersome, but we're going to have to use integration by parts. Usually I would skip this step and just move on to the next step and write down the answer, but there's a thing that I want to show you. So let's do integration by parts and do this step a little bit carefully. So I'm just doing straightforward integration by parts that you learned in your calculus class. Now we're going to go diagonal and across. Just like that. Let's write down those two terms. You get something like this. Straightforward integration by parts. Now, let's think about the first term. We need to evaluate this term between the lower and upper bounds. Now, the upper bound. As time t goes to infinity, what happens? The term that we want, which is t, which originally came from the function we wanted to take the Laplace transform of, t up here, grows linearly as t goes to infinity. So it's exploding on you linearly as a function of time. But it's multiplied against an exponentially damping term. So you have linear growth in time t, exponential damping, which wins. The exponential damping is stronger than linear growth in time. Therefore, the upper bound of this function will be equal to 0, because the exponential will really kill it off. And remember one of the very first properties of Laplace transforms as we talked about? We said that the function you want must be of exponential order or better. Better meaning it has to be growing more slowly compared to an exponential. So at most, it could be of exponential order. A linear growth is weaker than exponential growth, and therefore we're okay. But this is the reason why the example I gave earlier of e to the t squared doesn't work in this case. If the function we wanted to take the Laplace transform of was e to the t squared, you can see that if we replace t with e to the t squared and try to evaluate our upper bound, this is going to explode on us. The upper bound will explode because e to the t squared is going up faster, much faster, compared to e to the negative st is going down. And therefore, we always need to have e to the negative st win as it decays compared to whatever is growing, if it is growing. So in this particular case, the linear growth is okay. It goes down fast enough with the exponential such that the upper bound is 0. Now, the lower bound, t equal to 0. In this particular case, because we have a linear t out in front, that term also goes to 0, because time at time t equals 0 is 0. Therefore, this entire first term goes away at both the upper bound and the lower bound. Now, this second term over here, we can just directly evaluate this integral. because 1 over s is just a constant, and this is just an integral of an exponential where s is treated as a constant with respect to time t. So we could just directly evaluate this integral. We get this, and now evaluating the upper bound, e to the negative infinity is 0, minus the lower bound, e to the 0 is 1. So you get negative 1, which cancels the negative 1 out in front, and therefore we just get 1 over s squared. So apparently, the Laplace transform of the function t is nothing more than 1 over s squared. Remember, Laplace transform of 1 was 1 over s. So when you add a linear term, it becomes 1 over s squared. Now, you can imagine that this is already getting a kind of cumbersome and getting old pretty quickly. I don't want to have to do this Laplace transform every single time for every possible function in the universe. That would be really bad. So what we have done is to create a very convenient table, a lookup table, of all the functions that are commonly seen in science and engineering, and all the corresponding Laplace transformed function as a function of s. So now if we turn to the screen, you can see a table here that I'm showing from one of the textbooks, where on the left-hand column here, it represents the function you want to find in real space, little f as a function of time. On the right-hand column is the Laplace transform of that corresponding function, capital F as a function of the Laplace variable s. So row number 1, row entry 1, is the function equal to 1, the constant function. And we showed directly that it is equal to 1 over s. Right here on the board, just right now, I showed you that if the function you want to take the Laplace transform of t, its Laplace transform is 1 over s squared. Now you can do this for any number of functions, square root of t, e to the at. We also did that one. Row 7, e to the at, we also did that one in the context of the shifting property. And you could just keep going. It just goes all the way across. So this delta function, we haven't covered yet, but we'll cover shortly. It's a pulse function. Row number 15 we have covered. That is the Heaviside step function. That is the function where it stays at 0, and at time t equal to a, it jumps over to 1. And its Laplace transform is simply 1 over s times e to the negative as. Again, one of the shifting properties, right? Because row number 15 is Heaviside step function times the function 1. The function 1 has a Laplace transform which is equal to 1 over s. And whenever you multiply a Heaviside t minus a in real space, in real time, you shift by e to the negative s in Laplace space. Again, the shifting property. And the table continues over on the right-hand side, where you have more complicated functions like logs, sines, sinh and cosh, exponentials, time signs, and it just keeps going and going and going. And you have corresponding Laplace space functions over on the right-hand side. Now, this table that I'm showing you here is going to be your friend for the entire duration while we're covering Laplace transforms. And hopefully, as you go on to solve important science and engineering problems, this Laplace table will hopefully be helpful for you as well. Now, we're going to return to this table over and over again over the next couple of examples that we'll do. But for now, let's return to the board. And the next Laplace transform that I wanted to show you is going to take a major leap towards the use of Laplace transforms in differential equations. So let's take the Laplace transform of that special function that we're going to need to solve ODEs. Let's take the Laplace transform of an interesting function, the derivative of the function you want with respect to time, the first derivative. Seems kind of weird, but let's use the definition and see if we can make progress. Just using the definition. Now, we're unfortunately going to have to do integration by parts again. let's do integration by parts. Just like this. I've done integration by parts, where I've defined u as e to the negative st, dv as everything else, taken the differential element of du, we get that. Integrate both sides for v, you just get f. Therefore, you go across. The first term is just the function you want, little f of t, multiplied with e to the negative st, lower and upper bound, plus everything else, s times this integral. Let's first think about the first term on the right-hand side. At the upper bound, as t goes to infinity, what happens to the product of little f of t times e to the negative st? Once again, the assumption with Laplace transforms, and actually a very important property, is that the function you want to take the Laplace transform of must be of at most exponential order. So as f of t could explode, it may explode, but it has to explode less than e to the negative st. Okay? So if that is true, the upper bound here will die, because e to the negative st will decay fast enough for little f of t to not be able to compete. The lower bound at time t equal to 0, what happens? E to the negative s times 0 is just 1. So the exponential just becomes 1, and f is just evaluated at t equals 0. That's our initial condition. Little f evaluated at t equals 0. Okay, let's write that down. Now, the second term. This entire integral on the right is the definition of the Laplace transform of little f. Therefore, this is just s times capital F as a function of s. Just like that. So we've taken the Laplace transform of the first derivative of the function little f, and apparently that is equal to the negative of little f, the function you want, evaluated at initial time t equals 0, plus s, the Laplace variable, times the Laplace transform of the function f. Okay? So all of a sudden, magically, we've taken a derivative and converted it into an algebraic form. This is the magic of Laplace transforms. I think some of you are insightful, and you can see how this might be really useful for differential equations. We'll see that next when we do an example. Let me just write down this very, very important formula over here on the left so you can preserve it as we do the examples. So the remarkable thing about the Laplace transform acting on a derivative of a function is that a derivative turns into an algebraic form in the Laplace variable capital F as a function of s. Now, in solving ODEs, you've learned how to solve first-order ODEs, but also second-order ODEs. So we not only need the first derivative of time, but we also want the second derivative of time. So what's the Laplace transform of the second derivative of our function f with respect to time? Don't worry, just go through the procedure. Use the definition, then do integration by parts. You'll get a term that looks like this, plus another term. You unfortunately have to do integration by parts again on the remaining part, and then you finally get a form at the end. I'm going to skip that because I don't feel like doing integration by parts twice in the small board, but I'll write down the result over here. Conceptually, it's no different from what I just showed you for the first derivative. You just have to do it again. So I'll write down the final result for the Laplace transform of the second derivative. The second derivative Laplace transform looks something like this. We have negative Laplace variable s, the function you want, little f, evaluated at t equals 0. So that's your initial condition for your function t equal to 0, minus the first derivative of the function you want, little f, evaluated at t equal to 0. So as an example, this might be position, this might be velocity. It's the derivative, the first derivative of a position. So it's the scalar function you want, its derivative, both evaluate at 0. So Laplace transforms are very good for initial value problems. If you're given the position and the velocity of a ball flying through space, then you can evaluate the velocity and the position. Okay? If you're given initial conditions for both of the constants of integration, they just pop in directly into the form right here. And the last term on the right-hand side, we have s squared times the Laplace space transformed capital F as some function of s. I've boxed this. You might want to, at this stage, take a screenshot of this box because you're going to use these two formula over and over again whenever you're operating on a differential equation. I'll get out of the way so I don't contaminate the screenshot. Okay, all right, let's do an example. I'm going to erase all this and we'll write down an example that utilizes the forms that we have right here. Finally, we are ready to start using Laplace transforms to actually solve ordinary differential equations. Let's do an example. We have the function you want, little y, as some function of time t. We have a first order derivative plus 8y is equal to 8, given the initial condition that y at time t equals 0 is equal to the value 8. Now, let's try using our new technique to solve this equation. It's very easy. First, you apply the Laplace transform operator on the entire equation. Let's do that. So just simply take in the Laplace operator of the entire equation, and we just do term by term Laplace transforms. So the first term, Laplace transform of dy dt. Right over here. So let's just use this Laplace transform, which we derived using integration parts, but now at this stage, we can just directly use our final result. It would just be s times capital Y of s minus the initial condition of y at t equals 0. Just like that. The next term, 8 times little y of t, Laplace transform, is simply the definition. And lastly, we have the right-hand side, the Laplace transform of 8. It's 8 over s. This is a very common mistake that a lot of students make, forgetting the 1 over s factor. Okay, so once again, I've put a little comment here. Don't forget the factor of 1 over s. The Laplace transform of 1 is 1 over s. The first time you're gonna do this in the heat of an exam or a problem that you gotta do quickly, you're gonna forget this factor of 1 over s. I did it when I first learned Laplace transform. Everyone makes this mistake once. Just don't forget this factor of 1 over s when you take the Laplace transform of a constant. So now it's just term by term Laplace transform, where those three terms became these terms down here. So now, as you probably can see, we turned an ODE into an algebraic equation for the unknown function capital Y of s. And another cool thing about the Laplace transform is that at this stage, the initial condition gets seamlessly incorporated into the solution procedure. So we already know that y at initial time t equals 0 is just equal to 8. So we can just insert the initial condition right here while we're solving the procedure. Just like that. So we just brought down s times capital Y, 8 times capital Y. I brought the initial condition, substituted it equal for 8 because that's a condition that was given to us, brought it over to the right-hand side. So you know how usually when you solve an ordinary differential equation using techniques that you already know, you get a constant integration C or A or B, whatever you called it, that carries on throughout the entire duration of the problem. And at the very end of the problem, you say, okay, my initial condition was this. I'm going to substitute it and find my constant of integration. With Laplace transforms, it just appears right here. It just gets seamlessly incorporated into the problem. So at this stage, there are no adjustable constants. There are no constants of integration at this stage. You're done. There's only one unknown with one equation, capital Y as some function of s. Now, some students ask, what if you were not given an initial condition? You were given some y at some arbitrary time, t equal to 10 seconds, some other time other than 0 equal to some value. In that case, it's not an initial value problem anymore. It's something similar to a boundary value problem. Not really. I mean, the domain can go beyond that position x, or x or time, but it's no longer an initial value problem. In that case, unfortunately, you would just have to keep this around as a constant. So call this c or whatever you want to call it, just as a normal constant of integration, carry through with your procedure until the very end. You'll see that constant come until the very end, and then you would apply your condition as necessary to obtain what that constant c is at the appropriate time t that you're given, which is not at the initial condition anymore. So as you can see, Laplace transforms is an extremely powerful technique, especially for initial conditions or initial value problems. And that's why time is a very popular domain to transform into Laplace domain, because the definition of Laplace transform is integral from 0 to infinity. Time starts at 0, goes all the way to infinity. So it's the perfect technique to use oftentimes for a time problem, especially when you're given an initial condition. All right, back to our problem. So all we need to do is solve this algebra problem. So go back to your high school at this point, just do an algebra problem. Let's solve for capital Y of S. Just like that, we have our solution for capital Y of S. So now, we just did this part of the procedure. We took our ODE, Laplace transformed, we solved it for an algebra problem, which is much easier to solve. And now we have the final step. Do the inverse Laplace transform and go back to our real-time solution, because we're done in the Laplace domain. We have our capital Y as some function of S, which doesn't really mean anything to us in the physical domain because it's over in the Laplace domain. And therefore, to make some physical meaning out of it, we have to blast it back to the real domain by taking the inverse. So we just simply take the inverse of all the terms. Just like that. So of course, this first term will just turn into little y of t, because that is the definition of the inverse Laplace transform. And the right-hand side, we have two terms. The inverse transform of this term on the right, and then this other term on the right as well. Let's do each of those carefully. Now let's think about this first term over here. I'm going to rewrite it up here so that we can do this term carefully using the Laplace table together. All right, I've just written this first term on the right up here because I wanted to solve it carefully together using the Laplace table. So now if we go to the screen where you can see the Laplace table, all you have to do is compare the term that we want to take the inverse of and look for some function that looks like that on the right-hand side of the table, either here on the page left or over here for the page on the right. So if you go down the table, we're looking for something that looks like a constant on top of the numerator, and on the denominator we have s times the quantity s plus 8. So we're looking for something like that. So probably not these guys, because these are both s and s squared. You keep going down, square roots, probably nothing to do with it. The gamma function, probably not. So this comes close. 1 over s minus a comes sort of close, because we can set a equal to -8. And if a is equal to -8, then we'll capture one of the terms up here, which is 1 over s plus 8. But there's another factor of 1 over s hanging outside, so it's not quite this one. This one's also kind of close. There's an s squared, but it's the same constant a. We don't quite have that situation. So you keep going down, and then you stumble upon row number 11. This one right here that I'm circling, row number 11. So you look on the right-hand side. First of all, we're looking on the right-hand side because we're over in the Laplace domain. So we're looking for something that looks like the function we have that we can then transform back to the real domain. So if you look at row number 11, we have a minus b, which are both constants, divided by s minus a, s minus b. Okay, so going back up to the board, right here, we have the constant 8 divided by s times s plus 8. Let me just write down row number 11 right here so we can see it together at the same time. Okay, so this is row number 11, and this is what we have on the right-hand side. So you think about how could we make this true? First of all, this over here on the bottom left, s minus a, that could look like our function 1 over s on the bottom left over here if a were equal to 0. And if a were equal to 0, then I have s minus b over here, and I want that to equal s plus 8 on the denominator to capture the other term. So if b were equal to negative 8, we can make it map together. Just like this. So if a were 0, b were negative 8, then you can clearly see that this on the right-hand side exactly maps to the function, the term that we want to take the inverse of. So we know exactly how to go back because all we need to do is to plug in a equals 0, b equal negative 8 into this expression over here, and that is the inverse of the function that we want. Just like that. E to the a, which is e to the 0, minus e to the negative 8t. There it is. So we already know what our first term is. Let's write it down. Just like that. So now, the other term, constant divided by s plus a constant. Again, going back to the Laplace table. This one's a little bit easier because we saw that entry a little bit earlier. If you go to row number 7, you can see that this is a situation where we have a constant 1 divided by s minus a. So, of course, in this problem, the constant 8 can be taken outside, so that's no problem. And we have 1 divided by s minus a inside the table. So if a, over here in the board, were equal to negative 8, then we can exactly transform it back, and the real space function is nothing more than e to the at, which is just e to the negative 8t. Easy. Let's write it down. Just like that. So I hope you're starting to get the hang of how to use the table to invert it back into the real space domain. And it's so nice that we have this Laplace table because it really prevents us from doing integration by parts for every function, guessing to see what something looks like this and then trying to go back. Someone has already done that for us, so there's a tabulated table, Laplace table, that really comes to our benefit. So we have these two terms. Here, the Laplace transform of the first term on the right, Laplace transform of the second term on the right. Let's clean it up, and we have our final solution. And there we go. The function we want, little y of t, is equal to 1 plus 7 e to the negative 8t. So we just did our very first problem of solving an ODE, taking the Laplace transform, solving an algebra problem, using a little lookup table, and going back into the real domain. This is crazy. I mean, it still feels like black magic to me, even though I learned Laplace transforms a while ago and I've been teaching this for several years now. It still is absolutely mind-boggling that you can do something like this. We just solved an algebra problem. That's all we did. We did not solve a differential equation. We did, but it's just this crazy alternative route to solving a differential equation. So, summary of the steps. You have your differential equation. It's a hard problem because it's an ODE. You take the Laplace transform of the entire equation to take your ODE over to an algebraic equation using the expressions that we already derived for the Laplace transform of the derivative. Now you're in this Laplace domain and you're solving an algebra problem, which is very easy to solve. And now we have this function capital Y in the Laplace domain that we take the inverse of to try to get back into the real domain. And here, we just literally use the table, and out came our solution. Now, for some of you who saw this example and said, hang on, this is a linear first-order differential equation. Why are we even using Laplace transform in the first place? I could just use the integration factor. You're totally right. You're totally right. In fact, I intentionally chose this example so that we can check our answer and you can be absolutely convinced that Laplace works. So let's do the integration factor method to see if the answers agree. It'll just be done really quickly, but just wanted to show you that they agree. All right, this is the tried and true integration factor method. We just need to find our integration factor. In this particular case, it's just e to the integral of the coefficient 8. So we get e to the 8t. That's our integration factor. Our right-hand side, g of t, is simply the function 8. So you just use this expression, plug in the corresponding terms into the right places, and just directly integrate. You get something that looks like this. So e to the 8t canceled, it just became 1. Constant of integration c pops outside here. And all we need to do is apply our initial condition. At time t equals 0, y is equal to 8. So t equals 0, this term just becomes 1. Left-hand side is equal to 8. And therefore, our constant is just 7, which exactly agrees with what you have. So I hope you're convinced that the Laplace works. It is black magic, but for this first order ODE, you can see exactly that the method you already know how to do, integration factor method, agrees exactly with the Laplace transform method. The solution here is exactly agree. Okay, of course, I've specifically chosen this example so that we can cross-check with an easy toy practice problem. But Laplace transform doesn't end here. You can do much more complicated and harder problems that we can't have a simple method like this that you already know how to solve the differential equation. We're going to do more of that next. So keep all of this in mind, and let's start doing harder examples with the Laplace transform. Now, as you just saw in that example, the most challenging part of the Laplace transform technique is once you have a solution in the Laplace domain, after you solve the algebra problem, how do you come back to your real space solution? And it comes down to making your algebraic solution, the solution in the Laplace domain, look something like an entry on the Laplace table. That is actually oftentimes the most difficult and challenging part with a lot of these Laplace transform techniques. How do you take the inverse back? How do you massage the solution to make it look like something on the Laplace table? So let's do a couple of practice problems related to this procedure of making it look like something on the Laplace table, and more generally, taking the inverse back. Let's do an example. Let's suppose you did all that algebra in the Laplace domain, and then boom, out came a solution in the Laplace domain that looks something like this. So your capital Y of S looks something like this, and all you need to do is to invert it back to little y of t for your final solution. Now, all we want to do is take the inverse Laplace transform. So now there are a lot of ways to take the inverse, but for this particular case, it kind of smells like one of the shifting properties. In fact, it kind of smells like the secondary shifting property. Let's write that down. So this is the second shifting property. Remember, what we said in the second shifting property is if in real space, your time is shifted by a delay a, all you have to do is to go to the Laplace domain and multiply with a factor of e to the negative as. So let's rewrite the term that we have into something that looks more like the form that we have here. Just like that. So you can see that we're trying to take the inverse of this. All I've done is to just multiply the e to the negative s, just bring it outside so that it looks more like the exact form that we have here for the secondary shifting property. So we have e to the negative some constant times s times a function, capital F of s, hanging outside. Just like that. So now you can see the mapping of the inverse we want to take with the secondary shifting property. So we're almost done, but we need to be very careful with the time delay, t minus a. So first, let's just take the inverse Laplace transform of this function capital F of s. So what I'm doing here is first trying to take the inverse of our capital F of s function. This is the definition of the Laplace transform and the inverse transform. So now plugging in our capital F of s. Now, this one is worth remembering. If you go back to the Laplace table, in the previous example we just did, there's an entry on the table of e to the at, where e to the at Laplace transform is just simply 1 over s minus a. Therefore, in this particular case, a is equal to -7, and so this inverse Laplace transform is simply equal to e to the -7t. So this is simply row number 7 on the Laplace table. So the inverse of 1 over s plus 7 is e to the -7t. And this is the most important point. And this is where a lot of students get confused and make mistakes. Now, the function we just got, that is equal to little f at time t, right? I've just used the definition, and this is capital F. This is little f of t is equal to e to the -7t with no time delay. But to use the secondary shifting property, you see on the right-hand side that it is equal to the function f evaluated at t minus a. So we need to evaluate f not at time t, but at time t minus a. Just like that. So I now have f t minus a is simply equal to e to the -7t, but I'm going to plug in t minus a for t. And so it just becomes e to the -7 t minus a. And this is the function that needs to go into our secondary shifting theorem. Because ultimately, we're taking the inverse of this guy, which is going to be equal to just like that, right? So in this particular case, a is equal to 2, because we're multiplying by e to the -2s on top. So a is equal to 2, and we can just write down our solution because we know the right-hand side, f at t minus a, which is 2, over here as well, and we have our final solution. A equaled 2 in our particular case, because we have e to the -as, e to the -as is equal to e to the -2s, a is equal to 2, and now all we have to do is substitute a is equal to 2. It just becomes this, and we have our final solution. Just like that. So the Laplace inverse of this function is equal to the Heaviside step function shifted by time 2, e to the -7, again, shifted by t minus 2. So it's all about how to take the Laplace solution, massage it in the right way, find the appropriate inverse, be really careful about what the definitions are, where you're shifting by. And if you just follow the procedure, you should all be okay. But you have to practice. Math is a language. Laplace is a new language. You just have to practice. That's the only way you get better. Some of these examples are very tricky. You just have to practice. Okay, let's keep going with more strategies to take the inverse. And one strategy is called partial fractions. Let's get into that next. Suppose you solve the problem in the Laplace domain, and the solution looked like the following. S minus 1 on the numerator, and on the denominator, it's a product of two terms, 3s minus 4 times s minus 3. Now, when you think about trying to invert this function into the real domain, y, little y as a function of t, you think about it a little bit, and whenever you have a situation like this, where you have a polynomial function on the denominator, you can do what's often called partial fractions. The inspiration behind using the partial fractions is that in the original solution, it looks like we have a common denominator. So what we do is we take each of the terms in the denominator, create a new term by itself, not as a product of 3s minus 4 times s minus 3, but a summation of these separate terms. Now, what I've done is to have unknowns a and b, and if we choose a and b in just the right way, we can add these two terms together and recover our original solution. So let's think about how we can obtain a and b. The first step is to combine them to reproduce the product in the denominator. So let's see where the a and b goes when you do that step. We get this. So all I've done here is to combine these separate terms so that the denominator appears exactly like our original form. So I just multiplied things through. The term on the left was missing a factor of s minus 3, so I multiplied it on top, plus another constant b, which we're going to determine. It needs to be multiplied by 3s minus 4 in order for the denominator to look just like what we have up on top. So our goal is to find a and b. Now you realize at this stage that because the denominator here, 3s minus 4 times s minus 3, is identical with what we have up here, all we need to do is match this term on the numerator with this term and the numerator up here. So let's equate those two to figure out what a and b are. Okay, so on the left-hand side here, I've taken the numerator s minus 1, brought it down on the left-hand side. On the right-hand side, I've taken the numerator of the partial fractions form, and now we've equated them. And if we can find the right a and b to make this equality true, then we've accomplished our mission of achieving partial fractions. Because now we know what a and b are, we can divide the single term into two, and then now these two terms are much easier to invert from the Laplace domain into the Fourier, into the real space domain. So now you can really see what we're trying to do here, right? We're trying to make this easier because that's just an exponential, right? Inverse in the real time, these just turn into exponential functions. So we just need to solve this algebra problem by matching like terms. First, over here on the left, you see there's a constant -1, but also this function s, this variable s. Over here on the right, we have an as here and b times 3s. So we want to equate the s coefficients to be the same and the -1 coefficients to equal also the constants over on the right-hand side. Just like this. So we've equated all the s terms, brought it into one side, all the constants that don't depend on s over on the right-hand side. It means to have two equations with two unknowns, a and b. Let's just solve for a and b. All right, so we just solved for two equations with two unknowns for constants a and b, which were our unknowns. We just found them to be a is equal to -1/5, b is equal to -2/5. Okay, if you just check the algebra, you'll get this. My goal is not to test you with algebra. I trust that you can do two equations with two unknowns. Now, let's plug these constants a and b back into our partial fraction form, and then the inverse is now very easy. Okay, so this is our partial fraction form. So remember, this capital Y of s is now equal to this. It's a sum of two terms, and this multiplied through will exactly be identical to our original solution. So these two forms are identical to each other. It's just from a Laplace transform and inverse perspective, this is much easier to work with because we like things that look like 1 over s minus a. We've seen that over and over again because the inverse of that is just a exponential function. So just one quick modification that I'll do to this solution is to pull this factor of 1/3 outside in the denominator, because if we pull this 1/3 outside, it'll look like s minus a, which is the form that we want. So let's go ahead and rewrite this denominator over on the left, this first term, as just this 1/3 being pulled outside. So let's just do that real quick. Okay, so now I've pulled out this factor of 3. It just becomes s minus 4/3 on the denominator. Now, with this in mind, we want to invert. And if we go to the Laplace table that you can see over here, again, this is your best friend. You're becoming very good with reading this Laplace table at this point. So you look down, and row number 7 has an entry on the right-hand side that looks like 1 over s minus a. The inverse of that is just e to the at. So up here on the board, we know exactly what a is. For the first term, it's just 4/3. Second term is just 3. So we can invert it directly and write down our final solution. Just like that. So the function you want, little y of t, which is the inverse by definition of capital Y of s, is simply two exponentials added together. Because if you come up here to the Laplace domain, it's just two terms that look like 1 over s minus a with different values of a, and you get the prefactors, and you're all done. Now, it turns out that in many problems in science and engineering, you get exponentials in your solution. A lot of phenomena in science and engineering either decay or grow as exponentials. You'll see a lot of this once we start solving the heat equation. Everything is dominated by exponentials in sines and cosines. So that means that there are many situations in the Laplace domain that look like 1 over a polynomial product of s's. Like 1 over some s minus a constant times a different binomial. So it becomes very helpful for us to identify a uniform rule that we should apply regarding partial fractions. So let's cover that next. All right, so a general rule or rule of thumb for partial fractions. Like I said, you're going to have many situations where you solve the algebraic problem in the Laplace domain, and your final solution, y of s in the Laplace domain, will look something like a ratio of a polynomial on top, p of s, and another product of polynomials here, q of s. So it's a ratio of polynomials. And in many situations, you're going to have situations where the degree of polynomial of p of s is going to be less than that of q of s. So just giving out some examples. P of s up here might be a quadratic, might be s squared on the numerator, like s squared and s, so quadratic and linear terms on the numerator. The denominator might have a cubic term, s cubed, right? So in that case, the numerator will have a degree of polynomial equal to 2. The numerator will be 2, the denominator will be 3. So the degree of polynomial indicates what is the highest order of the polynomial term inside each of your numerator and denominator, p and q. And in many situations, you're going to have numerator p be less than that of q. If that were not the case, if the degree of polynomial of p were larger, you could just divide it out. You could just divide out your numerator, which might be s to the 5th, bottom might be s to the cubed. You can actually take that first term out such that you can preserve it back to this form again. It's a minor detail. Let's not worry about that. So when you have a situation like this, there's a couple of common scenarios depending on the nature of the denominator q of s. First, if q of s takes on this form, s minus a constant a raised to the nth power, right? We just did an example like that, right? In that case, what you're going to do is you're going to guess a form of y of s as a partial fraction as a sum of many of these fractions, and you go up to the nth power. So if your q of s polynomial is the degree n, you're going to have this go up to the nth term. So you're going to have n terms present. Okay? We'll do some examples, and you'll see how you can use this. But this is what you should guess, and you combine the a's through an, and you figure out what those coefficients are, just like we did in the previous example. So your unknowns are a1 through an that you're going to put back together and match it with the numerator p of s to figure out the a1s through an, just like we did in the previous example. Now there are another class of very common situations of q of s shown here. You need to hide, not that much room anymore. So q of s might look like this form right here. You might have an s minus a quantity squared plus another constant b all the way out here, the whole thing raised to the nth power. Also another common situation that we might find over in the denominator in the Laplace domain. In that case, you can still do partial fractions, but it changes a little bit. So let's first look at the denominator. On the denominator, you just take the stuff on the inside of q of s, which is just s minus a squared plus b squared, which is exactly you have inside the interior of your q of s. You raise that whole thing to the first power, to the second power right there, second power, and all the way to the power n. So it's got a parallel with case number 1, except you just have to take the entire Q of S, again, add as many terms as you need, in this case, to the power n. Now, the numerator, instead of just having a single constant, a1 through an, now you're going to have two constants. And you have to put a1 of s plus b1, new constants a2 of s plus b2, all the way till an and bn. Just like that, you'll keep adding more and more terms. You put them together, and you obtain what your a's and b's are. Now, in practice, one can use a numerical solver or a lot of lookup tables to figure out what these coefficients are, because it's going to get mathematically cumbersome, and a pen and paper calculation for all the coefficients a's and b's might become very cumbersome. But in general, this is the kind of guess that you should make for partial fractions if you are posed with a ratio of polynomials that looks something like this, which again, like I said, is very common in science and engineering. So let's do a couple of examples that illustrate the use of these rules 1 and 2. All right, let's just do some quick examples of what you would do with partial fractions. If you're posed with this Laplace solution, 6 divided by s cubed times s plus 3 quantity squared, then what you would do is you would identify the fact that you have a 1 over s cubed and you have a 1 over s plus 3 squared. So if you have two products, both of case 1, you would just take all of those cases and add them together. So in this particular example, this is what you would do. Just like this. So what you can see is that the first 3 terms right there belong to an expansion belonging to 1 over s cubed. And the next 2 terms belong to an expansion of s plus 3 quantity squared. So you can see how I adopted rule number 1, this one right here, this rule, where I've taken a polynomial degree. So in this first case, s cubed is a situation where this factor a is just equal to 0. So I have a1 over s plus a2 over s squared, a3 over s cubed. That's what I wrote right here. The second term is another case of case 1, where I've just taken s plus 3 squared with 2 coefficients, b1 and b2. And then you would assemble them back together, figure out what the constants a1, a2, a3, b1, and b2 are. 5 unknowns, you'll get 5 equations. That's it. That's all you need to do. Okay? It's cumbersome, but in theory, it's not so hard. Now, case 2, or example 2, right, which actually involves case 2. So this time, on the denominator, we have a product of s squared plus 4 and this other thing, s plus 3 squared plus 25, which is just 5 squared. So in this particular case, you'd have an application of the bottom one, where you can easily see that we have an s minus a squared plus b squared for this term right here, right? Where you have a is equal to -3, b is equal to 5. So we can definitely expand that very easily for that particular function. And then let's see what we get. So this is the first term, as plus b divided by s plus 3 squared plus 24. Because this is just a straightforward example of case number 2 down here with the power equal to 1, because this has just a power of 1 to it. So you just have one term in this partial fraction. Now, I did this one first because this term looks just like case 2. It turns out this one over here, s squared plus 4, is also case 2. It might not look exactly that way, but consider the situation where a over here is equal to 0. If a is 0, then we just have s squared plus 4, which is 2 squared. So b is equal to 2, and a is equal to 0, but it's still case 2 on the bottom. So let's write that down too. Just like that. So you'd have a sum of these 2 terms that you would guess in your partial fractions to make progress on your route to inversion back to the real domain. All right, at this stage, let's return to doing some more complete examples. All right, I know it's getting long, but let's just summarize everything by doing one more complete example from start to finish. Let's suppose we want to solve this second order constant coefficient ODE. I know that you guys already know how to do using constant coefficients. You find the characteristic equation, you find the roots, lambda 1, lambda 2, you have the three cases A, B, and C, you obtain those, you find a particular solution using method of undetermined coefficients or variation of parameters, and you evaluate your initial conditions. But we have this new magical trick, the Laplace transforms. Let's try that. So, initial condition of the function you want and its derivative at time t equals 0, and you have this ODE that you'd like to solve. Step 1 is to take the Laplace transform of the entire equation. Let's do that. Now, you take the Laplace transform term by term. This is where you want to use that lookup table for the Laplace transform of the second derivative and the Laplace transform of the first derivative. Let's write those Laplace transforms down. This would be it. Now, term by term. That is the Laplace transform of the second derivative. S squared times capital Y, Laplace space, function, capital Y, and then two initial conditions that pop out during the integration by parts. Second term, that's the Laplace transform of 4 times the first derivative of y, which is s times capital Y, the Laplace variable capital Y, minus the initial condition, the function you want, y, evaluate at time t equals 0. The third term, this one's pretty easy. This one's just 4 times the Laplace transform. This is just direct definition of the Laplace transform of the variable little y. And lastly, this right-hand side is just the constant 3 divided by s. Again, don't forget. Don't forget that factor of 1 over s for the constant. In the heat of an exam, oftentimes students forget that 1 over s. So don't forget that. Now at this stage, we can seamlessly use the initial condition to remove some of these unknown coefficients or constants. All of those terms are 0 only because that was the initial condition that was applied to us. Both the function, the position, and its derivative, the velocity, essentially, are both equal to 0. So those terms all go away, and ultimately all we have is an algebraic equation for the function capital Y as a function of s. Let's write it down. It will look just like this, where I factored out the capital Y, and this we can rewrite just like that. And therefore, our solution for capital Y is just this. So, because we have this, we like to use partial fractions. Let's use partial fractions. In this particular case, we're going to have a term for 1 over s, just by itself, and then 2 terms for 1 over s plus 2 quantity squared, using case 1 from the previous slide. So the case number 1 was the situation where you had something like 1 over polynomial that looked like s plus a quantity to the nth power. So we just have 2 of those, so we can just write down all of those terms together. Okay, so here are the terms. A constant a that we were trying to find over s plus b, s plus 2, c, s plus 2 squared. All of that must equal this guy, and so I just brought that over there. Okay. Now it just comes down to finding a, b, and c by taking the product, see what's missing from each term, and equate it with the numerator, which in this case is equal to 3. It will look something like this. I've just taken the numerator. This term is missing an s plus 2 squared. Multiply that. This b term is missing an s times s plus 2. The c term is missing a factor of s. Therefore, here, we're just going to have unknowns, a, b, and c. We're going to get 3 equations with 3 unknowns. Over here on the right, we have a constant of 3. And you can already see the constant. You're going to have 2 times b. Well, actually, in this particular case, everything is a factor of s. And over here, you're going to get a factor of s plus 2 squared. So you'll actually So it's not very easy. It's a little cumbersome. So you'll have to just combine all these terms together, equate it to the 3 on the right-hand side. You should get 3 equations with 3 unknowns for the constants a, b, and c. I'm going to skip that step because this just isn't an algebra problem, which I trust you can do. And write down the solution for a, b, and c, the constants. The constants are equal to 3/4, -3/4, and -3/2. 3 equations, 3 unknowns. You could do that. So if you plug it into the partial fractions form, all we're going to get is 3/4, 1/s, -3/4, the middle term, the right term on the right. So at this stage, you go to the Laplace table once again, and you look for each term. So 1/s is easy. That's just this term right here over on the right-hand side. That's just a constant. So the inverse Laplace transform 1/s is just a constant. The second term right here is like 1/s minus a. So that's row number 7 right here. That's going to give you an exponential to the at. In this particular case, a is equal to -2. And this final entry right here, 3, the third term on the right, is just simply going to be row number 8, which is 1/s minus a squared. In this particular case up here, a is equal to -2, and its Laplace inverse is a factor of t out in front times e to the at. So it's just the sum of those 3 terms. Let's write it down. And we get our final answer, just like that. Constant e to the -2t, t times e to the -2t. Easy. Just the beauty of Laplace transforms is it puts together this very systematic way of taking the Laplace transform, solving an algebra problem, and this is the most difficult part. Once you have the algebra solution, you have to use some kind of trick. I've used one trick called partial fractions to make the inverse easier because it all comes down to taking this solution and then massaging it in just the right way so that you can take the inverse easily using the Laplace table. That's what it comes down to. The whole reason why we're using partial fractions is so that it can make it look like terms on the Laplace table. That's the whole point. Okay, let's end here. Next time, we're going to cover this brief little thing called the convolution theorem, which is ridiculously important for a lot of numerical solutions of PDEs and ODEs, especially in the Laplace domain, Fourier, which we'll cover next. But we'll need to cover a convolution theorem, and then we'll actually start doing very important problems in engineering, like coupled system of ODEs. And we'll do a really cool example at the end of a hammer hitting an object, and we'll see the dynamics of that object go back and forth and see if we can solve that using Laplace transforms. All right. I hope you have a nice day or weekend or morning or whatever, whenever you're watching this. I will see you next time. Goodbye. See you then.